Hi everyone, welcome to the Astrophysics seminar. Today it's my great pleasure to introduce Professor Drummond visiting us from Cornell University. Drummond began his academic journey at Phil Hopkins University studying physics and math. And then he went to UC Berkeley and completed his PhD in astrophysics in 2018, working on the interplay of galactic winds and circumgalactic media. He then spent 6 years at the Center for Computational Astrophysics in New York City as a Flatiron Research Fellow. And this past July, Drummond just joined the faculty of Cornell University as an assistant professor. Drummond is known for his work on the CGM and the galactic wave, on which he also wrote a recent review article for the annual reviews of astronomy and astrophysics. And he has a broad interest in topics related to galaxy formation, high energy astrophysics, and machine learning. And today he will tell us about his recent work on bridging the divide, a multiscale approach to galaxy formation. Please join me to welcome Drummond.
Thank you, everyone. Wow, it still feels new to be Professor Fielding. This is exciting. So this might be my first talk where I was introduced as Professor Fielding. So very exciting for me. Let me start by saying, as Professor Fielding, I'm actively recruiting grad students and postdocs to Cornell to come work with me. So if you know anybody who might be interested, please send them my way. Excellent, and thank you so much for the kind introduction, although I didn't write any annual review article, so I don't know where that information came from, but I should double check that I'm not getting improperly. No, it's good. I did write a review article, it's just not an annual review article, and we'll get into that in a little bit. Okay, fantastic. So since today is Halloween, I included this image. I already quizzed half of the room and nobody was able to get it. This is my one nod to it being Halloween. So any last guess for why this is Halloween themed before I give you the answer? Okay, no one. Well, here's an AI generated version of the same nebula. If I go back, you can kind of see it right here, the eyes, here's like the triangular nose and the mouth. Jim is not impressed. But, I was gonna do an AI image only, but I thought, the real universe is so impressive, I would stick to that. So this is actually the Skull Nebula, or better known as the Rosette Nebula. We're not gonna talk about that at all. It's Halloween, so great. What we are gonna talk about is my efforts with some people here in the room to, do a multi-scale, make a new multi-scale model for how we approach galaxy formation on cosmological scales. So many of the people I've been talking to here are thinking a lot about very, very small scales, cosmic ray gyro radii, 1 AU structure of the ISM. That is another whole aspect of my research program that I'm very interested in, but we're not really going to talk about today. So we'll be mostly focusing on, large scale galaxy formation type stuff. Okay, let's all get on the same footing because I know, some people don't work on this at all. Very, very, very quick intro. Here's the universe at very high redshift. This is a dark matter surface density. When we evolve in time, okay, we get the famous structure everyone knows, the cosmic web. We get halos and filaments and all the fun stuff. And of course, living inside these halos are galaxies, right? In big halos, we find things like groups and clusters. In somewhat smaller halos, we find galaxies like the Milky Way. Good. I'm teaching Astro 101, can't help myself. These are actually slides from Astro 101. I know you're all more advanced, so let's get to the good stuff. The simple motivating question for many of us who study galaxies is this. When you add up all of the mass in stars in a given halo and compare that to the total available baryonic mass, it's much, much less, right? And this is, codified in the very familiar plot to everyone, I'm sure. Ooh, these labels are quite small. This is the stellar mass to baryonic mass as a function of halo mass. And what you can see here is there's this big gap, maybe 20% of the baryons in a galaxy like the Milky Way have been turned into stars. But in less massive and more massive halos, that fraction is, orders of magnitude smaller. And so this begs, this is not what I meant to do. This begs a very important question, why do galaxies form stars so inefficiently? And that is what I will try to take you through today, or at least, an effort to get at this question in a little bit more self-consistent manner. So I'll start by telling you the standard story, and in particular, why it's wrong. Okay. So the standard story. Here, what I'm going to show you is another cosmological simulation. This is one that includes baryons and star formation. It's from the CAMELS collaboration. You can't see that down there. I'm picking on CAMELS, but that's because they're my friends and they have, explored a lot of different what I would call standard feedback models, which I think are the culprit of what's wrong. So what you're going to see here is a cosmological simulation. It's a pretty small volume and it's going to flip around and zoom out and evolve in time. And what you'll see here is, galaxies form at the web, and this color is temperature. And as stars and black holes start to form, they eject mass and energy out of the galaxy, out into the surrounding medium, leading to these, hot bubbles, this hot circumgalactic medium that surrounds all of these galaxies. Okay, so the basic story here, which has existed since before cosmological simulations, dates back to, semi-analytic models, and is pretty much the same over the past, 3 decades or so, is essentially as follows. Gas comes into galaxies from the cosmic web. Some fraction of what enters forms stars. Some of it also feeds supermassive black holes, of course, although for this talk, I'm not going to spend too much time thinking about supermassive black holes, although much of what I'm saying does translate to higher mass halos where the feedback is dominated by black holes. Okay, so gas comes in, some of it forms stars, and the remainder gets launched back out in the form of a wind, of an outflow, right? And this outflow is powered by the energy released by the formation of stars, by successive supernova explosions, and by supermassive black hole accretion. Okay, that's the rough picture. These simulations do not have enough resolution, anywhere near enough resolution, to resolve what's going on in the interstellar medium of these galaxies. And so to get around this problem, what we have all resorted to is subgrid models, or just some parameterized model that, encaptures how much is formed in stars and how much is kicked back out. And the basic approach has been to tune these models, right? These models have free parameters. We can tune them until we can reproduce the statistics of galaxy populations, like the stellar mass to halo mass relationship. Robustly, across the board, for 30 years, when people have done this, including, the latest, greatest, state-of-the-art, cosmological simulations, notably the TNG simulations, which are sort of the current benchmark, find that they need to crank this knob all the way up to 11, in the sense that you need an outflow rate that is much, much larger than the star formation rate, particularly in low mass halos, Milky Way mass and smaller. So this is, in a sense, a prediction, right? What this says is that in order to reproduce the statistics of galaxy populations, we need mass fluxes in these galactic winds that are very high compared to the star formation rate. At least one order of magnitude, if not several orders of magnitude larger. Okay, well, this is a testable prediction. Okay, so we can confront this theory.
Statements like averaged over time, because there's a time dimension.
Yeah, that's a great question. So in the I'm making broad sweeping claims, obviously, because I want to get to my stuff. But you know, in TNG, to stick with the state of the art, there is very little redshift dependence on this ratio. So you know, and that's maybe a good thing, physically speaking, you know, it's the star formation, the details of the ISM, they don't really care about what's happening cosmologically. And so the amount of mass that's ejected per unit star formation probably shouldn't care so much. So in most models, this ratio is either weakly dependent or not dependent at all on redshift. Yeah. Good. Also, I'm, you know, fully intending to be interrupted throughout, so please, you know, jump in. I realize I'm gonna be covering a lot of ground, and half of these slides are new, so they may need some clarifications. They haven't been tested.
For the statistic here is exactly what?
Yeah, so there's any number of different statistics. The main one, the usual like first target, is the stellar mass to halo mass relationship. So what I showed to begin with, you know, how much the ratio of the amount of stars that have formed to the amount of available baryons. But there's also what's known as the star formation main sequence, which is the rate at which stars form relative to the stellar mass. There's the size of galaxies, there's the color distributions, there's any sort of statistic you want, you can calibrate to, and different groups calibrate to different models or different observations rather, but they're generally large statistical observations with, you know, many thousands of galaxies going in, not individuals. Yeah.
But they're also low redshift.
They're also almost all low redshift. Great point, Eve. Yes. Yeah.
Is the number of free parameters in your subgrid model less or greater or equal to the number of statistics that you fit that to?
Good question. So I would assume less. You know, because you have the stellar mass to halo mass relationship in a bunch of different bins. So that can each be considered, you know, its own observation. And the models, some of the models have tons of bells and whistles, but they're like, you know, 50, not thousands. And you know, I think that's probably more in the range of the observational constraints. Yeah.
So here for this plot, you would say if I take it even step back more, of course, if I were to measure this at super high ratio, I don't expect any star to have ever formed. So
Yeah.
if this was 0, no problem.
Yes.
So the statement is the universe is so old that this should have happened much faster, the formation of stars. So you should have exhausted it because the universe is.
Well, no, you're still continuing to form
I
stars.
know, but if you say there's an issue here, it's because you're saying this is not the beginning of the universe. So much time has passed
Yes.
that I expect order one. Where is that? Yeah, I guess there's some implicit assumption of.
Yeah, I mean, really, I think the simplest statement of it is that the gravitational freefall time and the radiative cooling time is vastly shorter than the Hubble time. So things should have already formed stars if they were going to, and something is preventing them from it.
So
Yeah, cool. Okay. So, good. So we have this prediction, right, that from most standard galaxy formation models, semi-analytic and cosmological simulations, you find that this ratio is very large. So we can, of course, go look at real galaxies in the local universe and measure this ratio. So here's the canonical example, M82. This is a nice multi-wavelength image showing the star. This is sort of like a edge-on nearby pretty low mass galaxy. This is the starlight here. And then there's this big biconical outflow traced by both H alpha and X-ray, indicating that there's this highly multi-phase outflow flying up out of this galaxy at thousands of kilometers per second. So the X-ray traces hot gas at, greater than 1,000,000 Kelvin, and H alpha is tracing, this warm ionized gas at around 10,000 Kelvin. This is the poster child for nearby local galactic winds, but there are many such systems, and they have had their mass fluxes measured in many different ways. And pretty much across the board, this ratio of the outflow to the star formation rate is in the opposite direction that is predicted by these standard cosmological scale models. Okay, sometimes this is like of order, but usually it's less than, sometimes it's much, much less than. And there's been a recent series of papers in the past few years that have really sort of nailed this point home that yeah, this ratio is much less than 1, not much greater than 1, and that is across the board. Okay, and so to my mind, this is a huge problem. And once I started looking at nebulas for the skull, I couldn't help myself. So this is the tension at the heart of galaxy formation. Here's our heart nebula. I think that's the last stupid one. No promises though. Right, but honestly, I think this is a really fundamental issue that people need to be aware of, right? Because we use galaxies to tell us things about cosmology and to try to understand the details of the gas physics going on in galaxies. And there is a massive discrepancy, right? And just to reiterate it, existing models only reproduce galaxy statistics, whatever the exact statistics are, but, large scale population-wide statistics with galactic winds that have huge mass flux. On the other hand, our best resolved observations find they have quite modest mass fluxes. And this is not, a factor of 2 discrepancy. This is a 2 to 3 order of magnitude discrepancy right at the core of our understanding of, the cosmic feedback cycle and how galaxies are regulated. And, this begs a crucial question, which is how do realistic, I should have made this bold, how do realistic galactic winds build realistic populations of galaxies? And that's really what motivates me. Can we take a feedback model that is consistent with our resolved small scale observations and have it lead to statistical populations of galaxies that are commensurate with observations? Okay, and so that's the goal for today, or really what I've been working on for the past 7 years. And on Friday of last week, I think that the paper is finally out. So this is like 7 years worth of work finally coming to fruition, or like part, 1 of like 8 is finally out. So good. The idea here is to put, a physics first, or really like a small scale emphasis first in our formulation of how galaxies work. Okay, so to do this, undoubtedly, we need to get the details of the interstellar medium and how stars form correct, right? And I threw this in because Phil Hopkins is around. This is from Phil's group, the fire simulations. And you can see, we're getting, these beautiful spiral galaxies. It looks kind of similar to a real galaxy. And so getting the details of the ISM is definitely something we're going to focus on, but we're also crucially going to take a much more expansive view of what it is to form a galaxy, because in the surrounding circumgalactic medium is where you have the interplay of inflows and outflows, which really is what is actually essential for regulating the fuel supply for star formation and black hole growth. So to put it simply, these galactic gas flows, I would argue, hold the key to solving this crucial tension at the heart of our understanding. Okay, great. So what do we need to do to understand these galactic gas flows? And first, sort of what makes this a hard problem? Well, in short, the title, right? Bridging the divide, multiscale, whatever I put. So galaxies and the gas in and around galaxies is shaped on cosmological scales, macro scales, megaparsec scale flows, like you can see here in this gas density distribution around, a halo with some filament. Obviously, we need the megaparsec scale flows to feed galaxies and to get the context in which they evolve. But as we've already talked about, feedback from within the galaxies is also crucially important. So if I zoom in by a factor of 1,000 to a different one of my simulations, here's a little patch of the interstellar medium. These are like the cold molecular clouds, and there's some supernovae that have blown up and are launching a powerful outflow. We need to get these scales right, in addition to getting these scales right. But as you can guess, it doesn't stop there, and you could obviously go to smaller and smaller scales forever. But in particular, in order to get the energetics and the mass fluxes and the phase structure right, we need to zoom in yet another factor of 1,000 down to the sort of sub-parsec scales where turbulence and atomic cooling regulate the overall energetics. And, with Philip and Matt and Jim and others, we're thinking, another 3 or 4 orders of magnitude smaller down to the AU scales where cosmic rays gyrate and all kinds of additional fun stuff. I'm not going to talk about that today, but I think this already illustrates the point that this problem is very challenging, especially computationally, because these scales are fully interconnected. So we're already spanning at least 6 orders of magnitude, probably more. And what this really means is if you're not getting the small scale stuff right, then your intermediate scale stuff is not going to be reliable. And so then your predictions about the macro scale properties of galaxies are going to be highly suspect. And so what I would argue is that, what standard feedback models try to do is they say, okay, we can't resolve this stuff, so we just put some box with knobs that replaces all of this. But as I'll get into at the end, the numerical implementation of the existing models actually precluded them from turning the knobs in a way that is actually consistent with observations. And so that's sort of that's the end punchline maybe, but that's what we realized through a long chain of wandering numerical experiments, which hopefully we will get to. So, okay, what we're going to try to do today is to bridge this divide. Great. So let's start in the middle. Let's start with a little discussion about the galactic winds and how they work, and in particular, some key insights that are going to be crucial for this macro scale evolution. So here's one of my simulations. Many groups have run similar simulations. I'm just showing this one because I have plots of it. But this is a 2D slice from a 3D simulation meant to represent a little patch of a galaxy that's actively undergoing a starburst. So I'm going to take this and flip it on its side and then make it a movie. Okay, so what we're seeing here is, the galaxy, this is the midplane of the galaxy. It's oriented vertically. The bright blue is the cold molecular gas. The black is the warm ionized gas. And pretty soon there will be some hot gas at 10 million or more. What I want you to imagine is a whole bunch of stars have just formed here, right? I just put this in by hand so we can do a controlled experiment. But imagine, a bunch of stars formed, something like this, a million solar masses worth of stars have just formed. And what's going to happen is the very high mass stars are going to start to explode as supernova quite quickly. And then over the next 30 million years, you'll have, continuous injection of energy from lower and lower mass stars exploding as core collapse supernovae until about 30 million years when, the last 8 solar mass star has exploded. We're not including any of the stellar physics. For us, it's just, injection of supernovae, very finely spaced in time, commensurate with some, assumed cluster mass in the middle. So let's look at what happens. Okay, boom, the supernovae start to explode. They inflate this hot bubble, which rips through on one side, and then the other, turbulence in the ISM continues to crash these waves over the super bubble that's exploding. Right, and this, I don't know, I love this movie, but this gives you an idea of how this process might actually work, and it gives us
It's called the accretion on this galaxy center. on the galaxy itself because there's like heating should increase the pressure, I guess.
Yeah. So, well, that I would say that's really the main motivation of doing this, right? In this simulation, let me just go to this. In this simulation, right, we just put stars in by hand, and then we see how much mass and energy are flung out. But the idea is that by ejecting these cold clouds from the ISM, they then wouldn't be able to form stars in some future generation. And crucially, the energy, this, lots of thermal and kinetic energy is flying up out of this galaxy. It's going to stir up the surrounding medium, and that will prevent future accretion, exactly as you asked. So you kind of just gave a spoiler for the big punchline, which I'm happy about, but which is really there's these two paradigms for how feedback can work. One is via ejection, taking stuff up and throwing it out of the galaxy, and the other is via prevention. And I think much of the community has focused incorrectly on ejection over the past, decade or so. And these simulations point to a model in which prevention is more important. But we'll get into that. Good. Okay. So let me give you just some rough characteristics of these from my simulation in particular, but also many others. Eve's, are the industry standard for this, the Tigris simulation. So I'll show some plots from theirs as well. Nice thing about this simulation is we can go and just measure some of the quantities that people see in observation. So the total mass outflow rate is less than the star formation rate, 10 to 50%. Great, that's consistent with our resolved observations, right? I showed you M82 and said that all the best observations show this. So that's nice. But we can also go much farther than what people can't really do in observations. For example, we can measure the total energy flux. Right? Measuring the energy flux is very hard in observations because actually most of the energy is in the hot phase, which is pretty much invisible to us. So here I wrote, maybe 50 to 100% of the injected supernova energy is carried out in the form of a wind. That's in this particular simulation. I think the Tigris simulations, maybe this is more like 10%, not 50%. But, regardless, a sizable fraction of the energy injected by supernovae is actually, it's going into energizing the ISM. Some of it is lost to cooling, but a large amount is flying up out of this galaxy into the surrounding medium where it can work to, limit the accretion.
I have a question. So
Please.
you have an injection, supernova injection, right? Do you just start from supernova explosion, or do you not care about anything about the massive star wind and radiation?
Fantastic question. So in this particular simulation, I just started from supernovae. This is a 6-year-old simulation. Many other groups, Eve in particular, have added all kinds of additional feedback prior to supernovae, handle the supernovae better. There's much more complexity you can add. These numbers don't really change a huge amount. And this is more meant to be sort of illustrative of the types of winds that we do get. But the amount of energy carried by winds and radiation can be significant. And I think will probably serve to boost these numbers for the energy. Okay, cool. Just a little bit of jargon because I know I am going to slip into this. I've already said it sometimes. These ratios, the ratio of the mass outflow to the star formation rate is called the mass loading factor, eta M. And this ratio over here is the energy loading factor, eta E. So we'll talk a lot about eta M and eta E later. But I want to show one other crucial aspect, right? These are very coarse measurements for such complex simulation, just the total mass flux, the total energy flux. So what people have done, I did this for this simulation, although this comes from Eve's Tigris simulations, have broken down the mass flux as a function of temperature and outflow velocity. Right? Because very clearly, look at this, there's hot gas, there's cold gas, there's intermediate temperature gas, right? There's a clear distribution. And that distribution, I'll argue, is crucial So you can see most of the mass is carried out by this cool 10 to the 4-ish Kelvin gas moving at like 30 kilometers per second. If we flip over to the energy, what you see is most of the energy is instead carried by this hot phase at 10 million Kelvin, moving at a few hundreds to 1,000 kilometers per second. So this, I would say, is completely robust across all simulation groups, pre-supernova feedback or not, is this, split between the cold phase carrying the mass and the hot phase carrying the energy. This does the ejective feedback, right? This is taking interstellar, material and flinging it out of the galaxy. And this does preventative feedback by heating the surrounding medium and limiting future accretion. And for reference, the, state-of-the-art cosmological simulations, like the TNG model, have a single phase outflow with a single velocity. Okay, that velocity varies with halo mass, with some, tuned parameterization, but it falls roughly here. So you can see they're not hot enough to get the hot phase, and they're not really cold enough to get the cold phase. So I think that is a crucial area for improvement. Excellent. So, I'm stressing the phase structure, right? How important it is to have the hot phase and cold phase. Well, what sets the phase structure? Are we confident we're getting it right? And this is where we're going to need to zoom in even farther onto, the skin of one of these interfaces, onto what I call the turbulent radiative mixing layer, or TRML, or turmoil. So sometimes I might call it a turmoil. Great, and what I'm going to show you is some work that I did with Eve a few years ago, and also a follow-up work by an excellent undergrad, now grad student at Santa Barbara. So what I will show you is just a simulation of some cool 10 to the 4 gas mixing with some hot 10 to the 6 Kelvin gas, like you would get at the interface of one of these, multi-phase patches. So there's some shear flow, and that shear flow is Kelvin-Helmholtz unstable, which leads to turbulence, and that turbulence mixes the two phases, right? And when you have cool gas, doesn't really radiatively cool. Hot gas doesn't really radiatively cool, but the intermediate temperature gas cools like crazy. So once you have this turbulent mixing, you get strong radiative losses just from this intermediate temperature regime. And that loss of energy leads to a condensation of fresh hot material to try to bring in new high enthalpy gas to make up for the loss of energy due to cooling. So that's sort of a schematic version of this. Eve and I worked out a nice, fairly robust analytic model to explain this in detail. But this is what you need. Shear flow gives turbulence, turbulence gives mixing, mixing gives cooling, cooling gives condensation. Okay, and so this is going to get, yeah.
Sorry, is the mixing dominant over, well, I assume there's not conduction here.
In this particular simulation, no, but we have done, Raj and I are working on this right now. Other groups have done this as well. Yeah. And it doesn't change the overall picture.
Okay, you're not just evaporating like that.
You can be in certain limits, undoubtedly. I think the point here is that the effective turbulent conductivity, like some V-turb times some outer length scale, can be much greater than the Spitzer conductivity. And yeah. Okay, so yeah.
Do you then expect to observe these radiation? And maybe the morphology of these?
Yeah, so these, resolving the morphology would be very, very hard. These are small. These are like sub-parsec, maybe in the Milky Way's halo. So people like Enrico Di Teodoro has these insane high-resolution observations of clouds, like this cloud, where he can resolve to sub-parsec scales and actually see this, very rough surface at the interface. But
So what's setting the scale of these structures?
yeah, that's a good question. We don't really know. We don't really know. I mean, effectively what happens is you have this bubble inflates, it sweeps up a shell. That shell fragments as it's expanding out due to thin shell instabilities, and it breaks up into different blobs. And these blobs follow a clump mass distribution function. So the most massive ones are, you know, some fraction of the disk scale height. The smallest ones is a very contentious point, which I'll get into in 1 second. But that's the roughly sets the scale. Okay, cool. So this is only one side of the story, right? In the basic picture here, this is that same or a similar simulation showing the cold gas opaque and the hot gas transparent. It's colored by the turbulent velocities. It's mostly just meant to be pretty. But the idea is that radiative cooling on the fractal surface, this highly bumpy, wiggly interface, where all the cooling is located, controls the transfer of mass momentum and energy from the hot phase to the cold phase. On the other hand, turbulent mixing is trying to shred and destroy these clouds, which is going to, you know, control the transfer of mass momentum and energy in the other direction, right? From cold to hot. So you can really understand this question of what sets the overall phase structure with just, you know, a classic theorists love it, timescale comparison argument, right? So shorter cooling times, the clouds will survive. Longer cooling times, clouds will be destroyed. And I know many people here don't think about, you know, the radiative cooling efficiency of ions at low-ish pressures around, you know, galaxies. So a little, just to be a little more concrete, what I'm showing here is the cooling time in mega years as a function of temperature. So the cool material here is like 10 to the 4-ish. And it's being heated by photoionization heated, so it's actually not cooling really at all. The hot phase is very low density and very ionized, so it's extremely inefficient at radiating. But when you mix these two via turbulent mixing and conduction, you populate this intermediate temperature regime, which can cool at orders of magnitude faster rates, right? And if we compare that to a cloud's mixing time, its destruction time, say, you know, a fairly large cloud here, right? Mixing time is just the size of the cloud divided by the turbulent velocity. So the bigger the cloud, the longer it will take to mix away. And so a situation like this, where the mixing time is much longer than the cooling time, we expect this cloud to survive and grow. And in the opposite limit, you know, if you have a much smaller cloud where the mixing time is shorter than the minimum cooling time, you expect the cloud to be destroyed. So I'm sweeping over like huge swaths of literature. There's lots of really fun, interesting physics at play here, but this is the rough picture, just the ratio of these timescales. Okay, cool. So just to show you that this actually works in a somewhat less contrived, still very contrived, but somewhat less contrived environment. Here are two simulations run by Matthew Abruzzo, former graduate student I worked with, now postdoc at Pittsburgh. And he ran these two simulations, otherwise identical. This cloud is 100 times smaller than this cloud. Okay, and it just so happens to work out that this cloud cools more rapidly than it mixes based on our model, and the opposite should be true in this one. So I'm going to start this simulation. The simulation will track the center of mass of the cold phase, so we'll stay with this cloud, and we're hitting it with a hot wind. It's going to develop a turbulent wake. The small one shredded and destroyed. The large one survives and actually grows, right? It's accreting new, fresh, hot material exactly as I described in that, you know, fractal picture, because it cools more rapidly than it grows, or than it's shredded and destroyed. Okay, growth, destruction, great. Okay, is everyone exhausted yet? We're done. Let's stitch it all together. Let's put it all together, and let me tell you some big punchlines. I mean, we're done with the zoom down. Now we're getting to the fun part. Okay, so Cool, I'm gonna put it together first in a sort of cartoon form so we can understand how the different pieces work. So here's our little galaxy, a bunch of supernovae explode. They heat gas up to millions of Kelvin, ripping through the galaxy at hundreds of thousands of kilometers per second. As it does, it sweeps up different cold clouds. And we know what's gonna happen, right? These clouds, some of them are gonna lose mass due to shredding, others will gain mass due to cooling. The small ones, they're the ones that are going to get shredded and destroyed. But what's extremely important to appreciate here is that this is not just the hot wind affecting the cold clouds, right? If you take tons and tons of cold clouds and hit them with a hot wind and shred them and destroy them and mix them into the hot wind, you're gonna change the overall evolution of the hot phase. So it's this two-way street that is really crucial. And the same is true also for the large clouds, right? The large clouds, they're going to survive, but they're gonna suck mass and momentum out of the hot phase and change its overall evolution, right? And this tells you sort of how much cold gas we expect to survive and the nature of the hot gas that's going to be leaving these galaxies. And that's crucial, right? Because as we've already talked about, these multi-phase winds are what we need in order to regulate galaxy evolution on larger scales. And so that's, really what this cartoon is meant to show is how we're including, the microphysics of the mixing, the mesophysics of the supernova injection and the multi-phase, everything, and then how this can come together into a picture that we can use for sort of macro scale evolution. Okay, let's go a little bit beyond a cartoon. Famously a bad idea to show like a wall of equations at a talk. So I'm not gonna go through all of these equations. I'm mostly just showing you this one because it shows that we did actually write all this down. We have a coherent model. It's more than just a cartoon. It encapsulates all of the physics that we just discussed today. What these particular equations are showing are the evolution of the velocity, density, and pressure of the hot phase. You can see all these fun source terms, and this is the other reason why I'm showing this, because after a long protracted battle with AppJ, I'm pleased to say I lost this battle and they didn't let me publish this color-coded equation, but I had to put it as like a figure in my paper. Terrible. The aesthetics are way off. But it's nice because if you look at this paper, and this is the review article that I was mentioning earlier, each of these terms, these colors correspond to the lines in the plots. I spent way too much time on that, but it's neat because you can see, the classic like adiabatically expanding wind, or you add gravity, or you add cooling, or you add, embedded cold clouds that are gaining mass, or embedded cold clouds that are losing mass. And you can see exactly how this changes the overall evolution. And writing this paper and playing around with this model was extremely fun, but also very much like a theorist's spherical cal. These are only radial gradients, and it was all time steady. Gave us a ton of intuition, but hasn't solved the overall goals yet. So going beyond that towards, a realistic model, right? Putting this all into a cosmological simulation. So the basic motivation was to take, some of the insights from the micro scale and the mesoscale, namely, the mixing layers and the hot phase and cold phase being split, and to make some model that would allow us to include this in cosmological scale simulations. Okay, so a little bit of a nerd moment here. This was from a collaboration called Smaug. Smaug is the dragon in The Hobbit, and Smaug cherishes the Arkenstone more than all other things, this gemstone. And so this model is the, whatever, don't bite me. But that's the name of our model. It's honestly more of, I would say, a framework than a model. It's a framework that allows one to include whatever whatever multi-phase structure you want in your outflows and whatever interaction between the phases you want. We put in my fiducial models, but this is a moving target. That's why we think of it more as a framework, because we'll continually update these as we, include better pre-supernova feedback, and as we, with Raj, for example, get better understanding of these mixing layers. Great. So, why hasn't this been done before? Well, there was two key technical advances that enabled this. One of them was not at all expected, and it turns out this was actually maybe the most important one. So, first, let me say this was work led by, I can't really see, this is Matthew Smith. He is a postdoc. We shared an office together at the CCA many years ago. He's now an MPA fellow, and he and I have been building this for a long time. And the first two papers came out over the past year or so, introducing this method. So the first one is on actually sort of counterintuitively how to resolve the low density phase. So the way most cosmological simulations work is they have some Lagrangian or pseudo Lagrangian approach where the resolution follows the mass. So the more dense you are, the higher your spatial resolution. But in these outflows, in particular in the hot phase of these outflows, your density gets extremely low. And so what happens if you have a fixed mass resolution and a very low density? Your cell gets humongous. And so that's what you can see here. This is a snapshot from a simulation. Here's our little galaxy, and the bad resolution, very good resolution. You can see this outflow that's coming out of this galaxy. You can see the individual cells. They're humongous. You're not resolving this flow at all. And people hadn't really appreciated this because people had mostly been focusing on getting ejective feedback, getting the mass out of galaxies, not the energy. And if this is carrying all of your energy, this low density phase, which is completely unresolved, what actually happens in these cases is the desired density, in the sense that like the fully resolved simulation would reach much, much lower densities than you're able to, because these cells can't get big enough. And so the density remains too high. Cooling is a density squared process, so you radiate away all of your energy. That is what's needed to do the preventative feedback. So Matthew, Greg Bryan, and I came up with a way to add just a little bit more resolution right at the base of the wind, right where you need the wind to actually get up out of the galaxy and do something to the CGM. It's sort of like an additional AMR criterion. It's just an AMR criterion that in essence, what it tries to do is maintain constant energy per cell instead of constant mass per cell. So if you have a very, very high specific energy cell that's super hot and super fast, you make it smaller. So you get higher resolution. And that's what's going on here. You can see, particularly right around the disk halo interface, the resolution is much higher. And it's a pretty targeted application of resolution. So it actually only increases the overall expense of the simulation by, 10 to 20-ish%. Actually, in the idealized simulations like this, it's like 2%, but in the cosmological simulations, it's more like 20%. Okay, that's one side why this hadn't been done before. The second was actually dealing with the cold phase. And so the characteristic mass of the cold clouds, getting at your earlier question, right? What's the range in cloud masses? Well, even the most massive cold clouds are much smaller than the mass of an individual resolution element in these sorts of simulations. They're about 10 to the 5 solar masses. These sorts of simulations have a resolution of 10 to the 6, 10 to the 8. So you're never going to resolve this with a normal simulation. And so we made some subgrid model, which are these ping pong balls flying up out of this galaxy. And each of these ping pong balls, which moves relative to the grid, represents a collection of clouds, these cool clouds, which, we saw Matthew Abruzzo's simulations of, right? And I described how these things mix. And so these cool clouds are constantly exchanging mass, momentum, and energy between the hot phase and this unresolved cold phase via this model, this turbulent radiative mixing layer model that I described. Okay, so those are the two technical pieces.
But I should think that you have two fluids or something that you're tracking, or two species.
Two species. Yes, there's another group out there that tried to do this with a fluid model for this cold phase. You know, it's sort of like people sometimes do dust as a second fluid. That actually doesn't work in this case because the volume filling fraction of the cold clouds is very low. And by having a fluid model in an individual resolution element, the cold phase can only have a single velocity. But what we often find is that you'll have some flying out and some flying in with a negligible cross section, so they should just pass through each other. So the two fluid models actually are sort of, I would say, fundamentally flawed for this approach, but it is a second, you know, yeah, not a fluid, but a second species that's being evolved, yeah. Excellent, cool. So let me show you this in action and then get to some final punchlines and realizing I'm running out of time. So here's that same galaxy. This is a very low resolution simulation intentionally, right? Because what we eventually want to do is use this in a huge cosmological simulation where we can't resolve individual galaxies very well. But this is just an isolated individual one for testing. And this is a galaxy chosen to be like M82, that canonical outflow that I showed to begin with. The right is TNG, the left is Arkenstone. You're going to see it's super different, incredibly different. This one is all ejective feedback. It's sort of like juggling. The gas is sort of flung up out of the galaxy and it just comes right back down and gets flung right back out, and it lives in this, you know, weird sort of cold, dark disk halo interface. This guy, very different, right? Blows this huge, fast, hot outflow that really disrupts the surrounding CGM. And what's very cool, right? This model was calibrated to reduce the star formation rate in a way that's, you know, gives you realistic galaxies. This model is able to regulate the galaxy to the same degree and yet does so in obviously a very, very different way. And so the basic idea, right, I've already hit this, I think, pretty hard. Hot phase does the preventative feedback, cold phase does the ejective feedback. And it's really that by separating these two phases, it increases the overall efficiency of both of these feedback channels, which allows us to regulate the star formation with lower loading factors that are consistent with both resolved observations and resolved small scale simulations, like the, you know, the tall box simulations I started with. Okay, cool. So final few minutes here, unless it's 54, so you can, you know, drag me off. I'll finish in like 2 minutes, I swear. Do this in a cosmological box. Okay, this is what we've been building to. This is what's, you know, 6 years in the making. The first step, what I'll show you, is actually not including the cold phase. We just want to understand just the impact of the hot phase. And then, you know, step 2 will be including the cold phase. This is Jake's paper. It just came out last week. It is finally Arkenstone in a cosmological simulation. It is meant to be impressively low resolution, as I said, because it's a huge volume, but it includes this micro and meso scale in the macro scale. Here it is in action. I can't tell you how satisfying it was to finally see this. But let me explain just quickly the fun stuff we were able to do with this. So here are energy loading and mass loading factors as a function of halo mass. The white line is TNG. So here's what motivated us, right? TNG has a mass loading factor of 30 at low masses, and yet observations show something like 0.1. And so what we did is we tried these different colored models and different combinations and just see what happens using this new framework. Without this new framework, all of the high energy, low density stuff would have overcooled. It wouldn't have worked. But with this, we're able to actually like successfully run these simulations. So here's just a one result. This is that stellar mass to halo mass relationship that I started with at z of 0. The observations are the dotted line. The white line is TNG in all of them, calibrated to reproduce this. And what you can see is the energy loading factor has a huge impact. If we crank up the energy loading, it pushes the stellar mass to halo mass down. If we increase the mass loading, it actually has the opposite effect. Higher mass loading leads to higher star formation rate, which is actually because you just have a higher density CGM, more cooling. And then finally, in this one, we change the slope of the energy loading. You can see how the change in the slope changes the slope in the stellar mass to halo mass. And so, as someone who likes to have control over my numerical experiments and understand this, it's very satisfying, right? Because we can directly change the small scale physics and see how it manifests on the macro scale. So I won't.
Sorry, can you?
Yes.
Can you explain these parallels that you chose? Like, do they have any basis, or is it just another knob?
Well, Eve and I are talking a lot about this right now. So you can make an argument based on the binding energy of the halo, which scales as 5/3 versus the mass, which scales linearly with mass, obviously. And so you can make an argument that your energy loading factor, which scales as the square root of the binding energy to the total mass, right, to get the velocity, that 1/3 should give you a linear slope here, which is roughly what we have. That's a very, very hand-wavy argument. There's actually been 3 or 4 really nice papers. In particular, these two are maybe the most fun I've ever had writing a paper with Mark Boyd, where we lay out a whole bunch of analytic arguments in a very, very simple regulator model that predicts, why you want this slope. But it's roughly that argument: binding energy of the halo to an energy. Yeah. So I'll stop here. Just very quickly, just flash up a pretty picture. This is the whole Arkenstone box, the gas surface density. If I flip over to TNG, you can see it's a little different. And if I put the ratio of the gas surface density, you can see Arkenstone has a much lower density in the immediate surroundings because of this preventative feedback, right? You've lifted material up out of the galaxy, up out of the CGM, and put it out into the IGM. So it's no longer coming into your galaxy to form stars. So I will end there. We have other stuff coming. Step 2 is the full model. It'll be calibrated to Eve's stuff. And I'll stop there. Okay, great. Thank you.
I apologize for the
Yes.
mistaken introduction. It's
No.
Yeah, I definitely encountered the article and somehow thought it was like an annual piece. Sorry about that.
No, it's good.
So we have about, sorry, the questions.
Yeah, so I actually have so do you plan to compare the micro and meso scale
Yes.
simulation to the observations in our galactic scale? Because you've shown, like, for instance, Hart Nebula, they do show a lot of evidence of what you're just talking about this
Yes.
too. Yeah, and then so you're going to compare that, and I have a question about that, because when you compare it, actual temperature of those molecular cloud and the periphery of the H2 region where you might actually see those micro turbulence.
Yep.
Temperature is much lower. So
Yes.
do you plan to then go down to that low temperature?
Yeah, so several groups have started to do that. That actually only it means we have to go, really far down here. And so what we started with, when Eve and I worked on this 4 years ago, was sort of an easy case where the cold phase, this is out in the CGM at low pressures, you're optically thin. The cold phase is only 10⁴ Kelvin. There are 100% plans. Raj is, I think, actively working on this to include, cooling down to lower temperatures. Raj is thinking about molecular gas in the intercluster medium, but of course, as you point out, the interstellar medium is right in front of us, and it's a great place to test this. I think we need a little more additional physics in order to actually make good apples to apples comparisons, but that is fully, on the agenda. Especially, I'm excited about LVM. I think LVM, the local volume mapper, is gonna be really exciting for this. These IFU cubes of all these structures will give us a huge amount of information on
The
this.
stars do form there.
Yeah, exactly. Yeah, great, thank you.
Yeah, I was wondering to what precision can determine the parameters like the mass load, event loading using the micro or mesoscale physics simulation so that you can get rid of the free parameter and
Well, we're gonna see. I don't know. So the step 2, which I kind of skipped over here, is to take the Tiger simulations, the latest and greatest version with all of the great physics, and then take the mass loading and energy loading factor and the full phase distribution of those, and put that in directly into the cosmological simulations and just kind of see what happens. I think there's always gonna, our model is not complete, right? We need to calibrate to something, and I think the underlying philosophy is to calibrate to the small scale and then predict the large scale, as opposed to the opposite, which is what's been done for a long time.
Yeah, I have a similar question. So finally you mentioned the density profile is lower in the center of the galaxy, right?
Yeah.
Yeah, so I remember like in the SZ observation seemed to show that the feedback is much stronger than the ENG model. I wonder how far is it you can compare your results?
Yeah, so fantastic question. My new colleague at Cornell, Nick Battaglia, is one of the experts on these, modeling of the SZ observations. So this is something he and I are. When's the AAG deadline? Really soon. We're putting in a proposal to do this in a little more detail. However, this is a small box. This is only 25 megaparsecs. Because we've only worked on the star formation version of this feedback. We're actively working on the AGN version that will include a lot of the machinery that I've described. But that does mean that for comparing to, the latest SZ observations, we're probably not hitting the high enough halo mass scales, because those are really the lowest masses that they reliably get to are like 10 to the 12.5, which is sort of our upper limit right now. But we're definitely, from both ends working towards that. Yeah, great question.
Final question.
Yeah, have you also thought about the supervarial phase that is being detected in the Milky Way halo, for example, in X-rays?
Yeah. I have lots of thoughts about the supervirial phase. Yeah. I'm gonna leave it at that. We can maybe talk more about that. I think, I think that has a lot of subtlety to how you interpret that data and how we would make any strong claims. I'm not feeling so good about that with these models, because I think in particular, the Milky Way today doesn't really have a ton of feedback. It's mostly just a slow rotating, marginally turbulent cooling flow. And I think you can get supervirial temperatures in that case, but yeah. Sorry, not the most satisfying of answers, maybe.
Let's thank Drummond again for your talk.